Okay, hello everyone who's decided to join it again. Thanks for coming to this next episode of Meet the meQuanics. The last couple of episodes have been offline, one of them due to technical difficulties and one because we were just having a conversation after a talk. This episode's going to be different. We've been lucky enough to organise a chat with a group of graduate students from the University of Bristol's Centre for Doctoral Training in the University of Bristol. So I'm quite happy to have 4 students who have decided to be gracious enough to sit down and have a chat. When they come up on screen, sort of from left to right on your screen, it's you and Alan, Jana Hinchcliffe, Sam Pallister, and Sam Mollett-Short. So thanks, guys and girls, for joining us.
Thank you.
So before we sort of get into the details of what you guys do and what you guys are learning and obviously what you guys are training for, maybe one of you or a couple, whoever wants to join in, give us a rundown on what these new CDTs are, because they seem to be a bit of a unique model to the UK at the moment. Seem to be a more focused effort for specific graduate training in certain areas of science. So whoever wants to jump in and try to give us a bit of a rundown on what the CDT structure kind of is.
So it's ETSA, one of the funding bodies in the UK. It's the only way they fund PhDs now. It's through these doctoral training centres. And the idea is, so I guess traditional PhDs used to pick supervisor and research project, and you went straight into the research group, and you did that project for 3.5 years, maybe, and then you came up with a PhD. Now the model is much more, there's projects from the general area, and ours is quantum engineering. And then we, for the first year, kind of loosely train in that kind of general specific area, get lots of skills, both theory and experimental, and kind of extra skills as well, like presentation skills. And then throughout that year, interact with local people in Bristol and external, and eventually, hopefully, after that year, find a supervisor in a research project, and then after that first year, start a research project. And then the next 3 years, it kind of ends up being a bit more like traditional PhD. But there's 10 of us per year that do that first training year, and then we all kind of separate off. And I think now we've kind of spread from physics to maths to engineering, so we've all ended up going in different places, and I think eventually the Bristol hope is that we actually have more go off into different universities as well, so it won't just be local to Bristol.
So these things are more tightly focused within a specific area. You know, you're not just doing a graduate program in physics, you're now doing a graduate program that's supposed to be targeted towards this new, field of quantum engineering.
Yeah, I guess one of the ideas is that you take advantage of economies of scale. If you have 10 students all together, you can get a lecturer in from all over the world to speak to 10 students, whereas it's quite difficult to do that on a one-by-one basis. So, for example, you have come down to see us. We've had Willie Hensinger from Sussex. We've had people from all over the world come over to speak to us, whereas that wouldn't have happened if it was just a single student. And having experience.
So, I mean, are you all Bristol people, or do you come in from outside doing your undergrad somewhere else?
I think we all did undergrad somewhere else, other than 2 people in the group.
Mm-hmm.
I was at Leeds for 4 years before I came.
Yeah, I was at Sheffield.
Yeah, I was at Imperial.
I came from Manchester, actually.
So Manchester, Leeds, Sheffield, and right.
Yeah.
So, I mean, did you guys study? I mean, what got you into quantum information? I mean, obviously the CQP in Bristol and the Bristol effort in quantum computing is actually, quite strong globally. Did you come in wanting to do quantum information? Was this sort of a focus in your final year of undergrad, or, did you get lured in because of other reasons?
So I did biophysics for my master's, and I was unaware of quantum tech until the very last semester of my master's program. It was an undergraduate master's, so I was doing research, but also still going to lectures, which is slightly different. most masters. And I spent most of my physics life really enjoying quantum mechanics, but not wanting to do it because I didn't think it was useful for anything. And then I had a lecture course on quantum computing, and it kind of blew my mind that this was a thing, and this was possible. And then I spent the next, so I took a year out after my undergrad and spent looking at UK universities that were doing research. And I think, like you said, the Centre for Quantum Photonics has a big reputation and popped up well in my Google search. And then when I came to visit, I saw the research going on here and got to hear about the people, and then they were talking about this new CBT. And it just, it seemed like a really kind of a good place to be at a good point.
What other alluring stories from the group?
Yeah, my undergrad was maths, not physics, so I did that, and I did a cryptography module that I really liked. So I was looking into doing cryptography, and I found a master's in it had a lot of quantum cryptography and the quantum text within it, and I decided that'd be more fun. So I did that for 1 year in Leeds, and then I really liked it, so I came here and carried on.
Well, my story kind of echoes Ewan's, I think. So I did theoretical physics for my degree, focusing on cosmology. I didn't realise that quantum mechanics was such an interesting field to go into. So I got into it at about the same time, right at the end of my master's year, in the second semester, and I had a course that was like on the foundations of quantum mechanics, and I got in through the theoretical physics group.
Yeah, I was always, during my master's, interested in quantum computing. I did my master's with Peter Koch, who's one of the sort of fathers of linear optical quantum computing, and so he said, go down to Bristol. I know a guy called John Rarity down there, and they've got this new CBT coming up. So I went down and had a look and enjoyed the group, but I guess I probably didn't actually realise the scale of Bristol's effort until I got in here and seen the midst. I think Peter probably downplayed it a little bit. Well, instead of biasing me to one place, he wanted me to see it for myself. So that was, that's where I came from.
I think the attraction is also, one of the benefits of the CBT is that you don't make a decision for the first year. You don't have to decide on your PhD with your supervisor. So you join, you have this whole year of learning about the subject, which at the time I didn't know much about. So it gave me that opportunity to really kind of invest time in understanding the field and get to know supervisors around the area and making sure that you hear horror stories of people going and joining supervisors and then hating it and leaving or whatever. So that was an important thing for me. I had the time to spend understanding the subject area, finding the bit I really enjoyed, and then finding a supervisor that would work well with.
So none of you have actually come up through sort of the experimental physics side. We've got bio, mathematics, well, Peter Koch, who's a theorist. And again, so none of you have really come in sort of from the experimental side of physics. You've all come in from other areas.
We do have some people in the group which did come through experimental. Alistair did his master's with Winnie in Sussex doing ion trapping. And so he was doing experimental quantum information computing before then.
It was experimental biophysics, so there's a lot of optics, which I was doing mostly on imaging systems and some computational stuff. So it was vaguely, it wasn't completely random. Yeah, there's quite a spread between a spread of chemists to computer scientists, a couple of, or maybe three experimental physicists, a few theorists, and then a general mathematician.
And an engineer.
And an engineer, yeah.
Well, I mean, the engineer's okay. I'm not sure about the mathematician. But I mean, Bristol's kind of marketed itself, especially through this CDT on quantum engineering, sort of training the next generation of information technologists and information engineers. I mean, was that a big drawing card as sort of where you would see a future career going, or was it really you were just interested in this particular field of physics?
I mean, I didn't really know going into the quantum engineering program whether or not I really wanted to stay in academia or go as a researcher or go into an industry research group or even into a startup technology. Actually, one of the nice things about the CBT is you really got to see what it's like to have a career in those kind of areas. And you get put in touch with a lot of people who come from those areas. So yeah, I kind of see myself moving towards maybe startup new quantum tech area, maybe spending some time in academia, but it's quite exciting to be in a field which is at that kind of turning point of coming out of the lab and really becoming a technology that is getting used and getting developed and getting produced.
Yeah, I mean, I didn't necessarily know at the time, maybe you guys did, but we kind of, I think, hit the sweet spot in joining the field because it's right on the cusp of being taken over by enterprise and computers starting to sit up and take notice.
Yeah, it's almost like somebody planned it.
Well, if we planned it, we did pretty well. We're never too sure about 10 years ago if the money was going to fall out of this, but luckily enough, it hasn't.
I guess I'd also just like to echo what you said a little bit earlier about the difference in how you would pick a PhD maybe at the beginning of the first year of CT at the end. I mean, when I started doing it, quantum error correction was kind of like the most boring thing in the world that I could study, because who wants to just correct errors? You want to actually do the thing faultlessly.
Well, thanks for that. That's my entire career.
But I'm actually now spending my next 3 years researching quantum photonic architectures, of a large part of which is basically doing error correction before the logical scale. And that I found that fascinating, and I don't think that I would have been able to make such an informed decision if I hadn't had that year of oversight. And I kind of count my lucky stars that I didn't just go straight into a PhD project and then realise, oh, I wish I'd done something else. So that was, yeah, good benefit.
So this initial first year of sorry, continue.
No, go on.
This sort of first year of initial sort of exposure to where the field's at and what people are doing certainly is useful when it comes to sort of focusing where you want to go.
Yeah, you spend your first year in CET realising how little you know about anything, and that's good. That's really good, because I guess the gap between what you, especially in quantum engineering, which isn't maybe just a single area, it really spans a whole breadth of experimentalism, material science, engineering foundations, everything. You just don't have that time in your undergraduate or even your master's to get to a proficient level where you can make informed decisions. You just need that extra year.
So what's the progression? So you do a 3-year undergrad and then you go straight into the DTC, or is it a 3-year undergrad, then a 2 years master's, and then into the CDT?
Most of us have a master's as well. I think we all do.
Yeah, it's not required to have a master's, but I think the majority, we probably all have a master's.
So all 4 of you have a master's before you came?
Yeah. Some of us have too.
Yeah.
So are you all intending to go into sort of the photonics engineering? I mean, how many is sort of going onto the theoretical side that may not exclusively focus on photonics, which is what Bristol does, versus how many of you are looking to move into the lab as part of your major PhD projects?
So I'm not affiliated with the photonics effort in Bristol at all. I'm actually based in maths, and Bristol has a reasonably sized theory group that's entirely separate from its efforts in CQP. So I'm not interested. Well, maybe that's too strong a word. Maybe, yeah, photonics is not my area of expertise, I'd say, and I wouldn't say it's the sole focus of the CBT that to feed directly into Bristol's photonics effort. I think it's really training a much broader class of PhD students.
Yeah, I'm kind of a bit separate from the main group as well. So I work with quantum dots, but I'm not doing any integrated photonics like most of the group.
Right. So, I mean, who is going down into the lab, or are you all moving away to something else?
Me, I guess, would be I'm the CQP lab representative for this.
Okay.
Yeah, I actually work. I straddle both doing bulk experiments and working on the integrated photonics side. So I'm essentially trying to do both both trying to do my one experiment, but in two very different ways, on two very different scales.
So you guys are all intimately involved. So not only the efforts in Bristol, but obviously the quantum hubs that exist in the UK, and this major research effort. This has sort of turned into a much more national sort of goal when it comes to developing quantum technology. Now, Bristol itself doesn't quite have a hub, but you guys are certainly involved with many of the other hubs that are based throughout the country. Do you interact closely, especially as part of the CDT? Certainly the more senior researchers, senior postdocs and whatnot, I imagine would be more involved, but do they try and get you in at this sort of ground level and sort of ship you off to Oxford or ship you off to Birmingham or these other places?
So I guess there's quite an effort in the first year of the CDT to make sure that we have all of our options open, and so we can kind of choose whether or not we want to interact with the Bristol Comms Hub or any of the imaging stuff. There's someone, a student who's just finished a stint down in Sussex. I've been working on some ion traps with Winnie, and we've also, well, at the moment we've got a student in QET Labs as well, working with some people over there as part of their research.
Got one out, so
as well. Yeah, so they make sure that in the first year you don't necessarily just become another CPD PhD student, but obviously if you want to do that, then you are in a great position to do so.
I think interestingly as well, the funding for the CBT came 6 months prior to the decision that there was going to be this national effort with lots of hubs, which means that there's no formal connection between the CBT and the hubs, but there are individual connections that you make via your PhD project.
But I mean, there is that kind of flexibility that, for example, if you wanted to go work in quantum communications, obviously there are these links to the hub in York, and you can obviously collaborate with them even though that you're still physically in Bristol.
Yeah,
there are work. So each hub has 4 or 5 work packages, they call it, which are kind of sub-main projects that they're all working from. Bristol is actually leading, I think, 1 of the imaging or 2 of the imaging work packages, and 3 of the communication work packages. So there's actually an awful lot of work in Bristol going on, and an awful lot of resources available for equipment and manpower. So it's definitely, at least from the communication and imaging side, it's very, very full of opportunity to get involved with that stuff. And then I think, at least for getting involved in the other hubs, it's pretty easy. It's CDT students are already paid for by the CDT, so you find a supervisor. It's relatively easy to get, as long as there's a working relationship and a project available. It's not that hard to get. You're already funded, so supervisors are pretty happy to take them.
Yeah, as far as a professor's concerned, you're free work, so it's always useful. So I mean, sorry, go ahead.
One of our students had us the price at the moment working on setting up one of the work packages for the Quantum Communications Hub, which is setting up a local Bristol quantum network. So yeah, we're going into that.
Oh, so you're setting up a local network in Bristol, like the Tokyo network or the Vienna network or something like that?
Exactly. There's going to be a local network in Bristol, and then soon that will be connected up to places in Cambridge. And
so it's going to go from Bristol. There's going to be a few nodes in Bristol, and then that's going to go on one long track into London. I think it's either Imperial, UCL, or somewhere in London, and then that's going to go north up to Cambridge.
And this is a QKD network or a full quantum communications network?
So that's a QKD network, and it's quite interesting because it's based on, there's a dark fiber network in the UK, so it's also used by a lot of classical communications, which I think is the interesting research part of it, is that they're trying to work out how to integrate quantum on fibers that are already being used for classical comms.
Okay.
Non-trivial task, I believe.
Must admit, that's the first I've heard of that. I didn't realize you guys were building a QKD network as well. It'd be 4 or 5. More expansion of these networks is always a good idea. So, I mean, if we can sort of rattle down the line from you and down to Sam on the other side, is to, I mean, you guys are all first years, right?
Second years. So we've already picked up PhD research area.
Awesome, because that's what I would like you to try and summarize. Where are you going? What projects are you looking at?
So I work with Jonathan Matthews, who is leading the sensing or metrology effort in Bristol, here, along with John Rarity, actually. And my particular project is on using a material nonlinearity called Kerr nonlinearity to produce states of light that are useful for metrology scenarios. And that's my bulk experiment. That's what I'm trying to produce in bulk, which involves firing pulses through, high power pulses through fiber. And then the integrated part is actually the state of light I'm producing for that experiment is actually a squeeze state, it's a squeeze vacuum. It's very useful for trying to get it on chip. So that's what also got my work.
So I mean, we spoke last week a little bit with Seth, and he also brought up this term quantum metrology. Could you expand a little on this as to what is? I mean, first of all, what's metrology? What's quantum?
Sure. So I don't like using quantum metrology as a word, because so metrology classically is measuring standards. So like the National Physical Laboratory or NIST in the US, they work on finding standards of time and weight and things like this, and that's what they would call metrology. That's what metrology is for them. Quantum sensing, as I like to call it, is really is trying to find a way of using some part of quantum mechanics to get some improved accuracy or precision actually with your measurement. There's a quantum sensing hub, and there's also a quantum imaging hub. There are two separate hubs. The sensing hub is really actually just using quantum-based systems to get just as a mechanism for measuring something. So they've got these gravity sensors. Which they work really well and they're better, but they're not eating. If you could come up with anything that was based on classical mechanics, there's nothing to say that you couldn't just have a classical sensor that would do just as well. But the quantum imaging hub, at least part of it, is trying to get beyond what we call there are some classical limits which are defined by quantum mechanics, where if you use a laser light and you're trying to measure something, no matter how hard you try, there's some fundamental noise in the experiment due to quantum mechanics. And then if we introduce quantum states of light, particular quantum states of light, then we can actually get a reduction in noise, which means we have pass the same amount of photons through our experiment, and we can actually make a better estimate of what's happening in the two. So Bristol's effort is focusing on absorption measurement. So you fire laser light from something that's absorbing light. If you do that with a laser or a coherent state, then you get some amount of precision, but then if you use a Fox state, for example, you get an improved precision. So if you have a limited number of photons you can fire through, then you do better if you have a Fox state. So it's just trying to use some element of quantum mechanics.
And this is actually quite important. I mean, this is actually quite important, as we've discussed on other episodes. For example, last week there was another announcement from LIGO that we've detected the second set of gravitational waves from an emerging black hole. They're actually trying to employ these techniques of using sort of quantum sensing or quantum states to enhance these measurements, correct?
Yeah, absolutely. And that's probably the prime example of quantum sensing. Yeah, I would say they've got their interferometer, and at the moment it works with laser light. And then there was it was the first result of quantum sensing actually was Carlton Higgs back in sometime in the 80s. So if you actually fire in a particular state of light called squeeze vacuum into the other part of the interferometer, then it means you can better guess the phase change that's going on, which obviously LIGO are very, very interested in doing. So that's a prime example of the kind of things we're doing. So that's phase estimation. We're working with absorption, but it's the same principle.
So Jana, how about you? What's your project?
So I'm working in the quantum dot group with Ruth Alton and John Rarity. So we're looking at a different model for quantum computing. So it's not gate-based or measurement-based. It's an ancillary-driven model. So you have like an external particle, and that will control your quantum registry. And we're looking at how to apply that to quantum dot systems. So we're going to use like an electron spin and quantum dot as a kind of ancilla. And then we're going to use that to manipulate the nuclear spins within the quantum dot. And we're looking at how that would work. So it's mainly theoretical at the moment, but I'm working on experiments for how to do the measurements for that.
So do you expect yourself to be in the lab, or are you really on the theory side of this?
No, I do quite a lot of work in the lab. So we've been working on how to do quantum non-demolition measurements in the lab. So we're using a phase shift setup to do that. So, and then depending on the state of your electron, you can use that to tell you the phase you picked up, and that can tell you what. So if you use a photon to interact with the electron and give it a phase, then you can use that to tell you what state your electron's in without actually measuring the electron in any way. So we're trying to do that sort of measurement in the lab.
So in terms of the technology that you and Ruth and John are pursuing, in terms of, you know, the major quantum dot groups are people like HRL, Maryland, Andrew Zurak at Sydney. How far along in terms of your technology do you see things are? So do you have a qubit? Do you have controllable 2-qubit gates? Where do you see quantum dots, particularly at Bristol, fitting into not only sort of the worldwide effort on quantum dots, but in comparison to other technologies such as ion traps, optics, superconductors?
So our work isn't really using quantum dots as qubits. We're, at the moment, our experimental work is more things like single photon sources and phase shift, so switching polarization of light using quantum dot as a Faraday rotation. So we're working towards getting a high phase shift using the quantum dots, and I think we're getting some of the highest phase shifts we've seen before now in the quantum dot sector. So on that side, we're pretty far ahead.
Oh, so your system is more of a hybrid model where you want to try to use quantum dots in sort of traditional optical quantum computers.
Yeah. Yeah, it'd be more for a hybrid. We're not really specifically working on making qubits in the lab.
Okay, Sam?
So officially my project is on verification of quantum devices. So this could be verification and validation of a particular quantum state. So if you could have a black box that's spinning out some state, so it could be the state of light that you're interested in metrology apparatus, and what you've got to do is you've then got to verify that you actually have that particular state. Or it could be, from a quantum computing perspective, it could be that you run some computation and you've got to validate that your computation was carried out effectively. So most of the time I do that from the theory side, working out schemes and strategies to do that in the most efficient way possible. But I also work on quantum algorithms, like 25% of the time.
So in terms of verification, I mean, you obviously trying to verify things at the device level. Does your work feed in much into sort of verification more at the compilation stage? So if I have a quantum algorithm that I want to compile into a quantum circuit that I then want to implement in some error-corrected or non-error-corrected system, there's certain levels of verification that have to occur at each step. Are you looking at that all, or is it just sort of, okay, I've got a qubit, I've got to characterize that qubit, make sure the qubit's working the right way?
Well, you can like you said, you can split it down into lots of different steps. So you can characterize and verify this thing at all different stages of your device, from the top-down approach or from a bottom-up approach.
Mm-hmm.
In principle, I'm still working on the very bottom layer of just having qubits doing some, sense of some kind of operation on them, and then you've got some state that you want to verify what you've got. That's not to say that you can't do the higher levels of architecture of verification and validation. It just feels at quite a young stage. So in principle, it's possible, and I think it will come, but it will take a few years before we get to that stage.
At the moment, are you marrying yourself to any particular technology, or are you just looking sort of in broad strokes that could be applied to anything?
So these guys want me to say photons, but no, I'm completely platform agnostic at this point.
And also, to be fair, the way you encode the qubit is relevant. So validation, verification at that very low level, you probably wouldn't be getting. You want to make sure you're producing the right photons, then you want to make sure you're producing. And also, especially with photons, we don't encode them in a normal way. You don't have a qubit in the sense that an ion trap has a single qubit.
Yeah, sure. And the strategy used to verify these things has got to be constrained by the limits of the technology that you have. So, in that sense, like at that kind of compilation stage, there is going to be some input from what your architecture is and what your platform.
Yeah, so the basic idea that you do have a two-level quantum system of some description that you can probe both of its levels, and those kind of standard qubit operations.
Yeah, sure, but then there's this whole discussion about what's physically plausible for the verifier to have access to. Is the verifier just doing measurements at the end? Is the verifier like controlling some of the computation? Does the verifier just get a list of like a ticker tape output of what's been going on in the system? So you have to kind of marry up what you can expect to be able to do with your device and what math says will be the best thing.
Mm-hmm. So Sam?
So I work on quantum photonic architectures, specifically integrated photonic architectures. So I work with Hugo Cable, Terry Rudolph, but also other photonics guys such as Mercedes, Segovia, and Pete Chappell. So they're actually probably everyone that I work with, because it's quite a small effort at the moment. So essentially, the analogy I like to use is if you want to build a house out of bricks, but all of the bricks have cracks in them in kind of an unpredictable way, you can do that, but you have to use more bricks than you would normally want to use. So your classical brick is great, it works really nicely, and it's been worked on for 50 years. But the quantum brick at the moment is still very fragile. And CPP is spending a lot of time, effort, and money making it less fragile, but quantum states are naturally very fragile. And the technology is to some extent at an early stage. So you can consume more of that brick to make a house that doesn't blow over in the wind, but you have to do it in a clever way. You can't just throw more stuff in it. And really, it's quite fun at the moment because there are loads of low-hanging fruit. We have the kind of general idea of how you would make this computer. You would generate this big cluster state, what we call big entangled set of qubits. And we do this in a way which is percolated. So because of the nature of entangling operations in photonic schemes, they're probabilistic. So we can't ever tell whether or not a single entangling operation is going to work. I mean, that would be great if someone with quantum dots could do this deterministically, but at the moment, in the full photonic sense, it's not. So we operate above a percolation threshold whereby we know that statistically we're going to get a cluster state we can convert into something which can be universal. So in that sense, we make something which is unpredictably good and bad, and it's about hacking away at that and remodeling that into something which is actually useful. And what's quite nice is there's still, as I said, loads of low-hanging fruit, because in theory, we have a model that we know all of the steps, but at each step there are optimizations that we made. There are lots of questions and potential areas that we can improve on. And so that's quite exciting to work in at the moment.
So, I mean, in the context of certainly optics, and actually our very first episode of this was with Jeremy, certainly you guys are all within the CDT and within the CQP, so you certainly get exposed to a lot of it. You also see these results coming out of Martinez's group at Google, IBM with their quantum experience, Delft, even the other hubs around the UK, whether it's the ion trap guys at Oxford and Sussex or the other people around Europe. Certainly within the core technology that Bristol is focused on, which is linear optics, how do you see it stacking up? Certainly from a student's perspective, as you're just coming into this, you're exposed to all this advanced technology that is getting newspaper articles every week. in terms of sort of your outlook of where photonics is, where it can go, and how it can compete, where do you see the benefits, and where do you see the work still needs to be done?
So I kind of like to see photonics as the underdog at the moment, because in the US it hasn't necessarily had the funding that ion traps and superconducting quantum computing has had. But hopefully we're going to see a shift towards us if we produce more goals, more output, and show actually that it's a viable method of computation. Actually, one of the lines that people like to use about integrated photonic computation is that our problems are on the small scale and not on the scaling up. So, for example, with Martinez's device, which is fantastic and it is the best in the world right now, and I can't speak highly enough about his device, but they're going to have a real problem going to a 2D lattice from a 9-qubit linear one to go into a grid. And so that's actually a really difficult architectural problem. And the same thing goes with ion traps. I mean, if you're going to be interacting with things locally, how are you going to do that with photonics? You're going to have to make good couplings. So actually scaling up the system might prove difficult, but I'm sure they'll crack it somehow. Whereas with photonics, because we're using fabs and devices which have been developed using silicon manufacturing anyway, a lot of the times our problems are on the individual devices making a really good low-loss switch. If we can make a really good photon source and a really good low-loss switch, that would be a large amount of our problem sorted, because we can print this thing out large, and the way that we do quantitative computation is we only need local interactions. So that's quite a nice way of thinking about optics, linear optics, and also it's nice to think of yourself as the underdog.
Of course. Look, I've still got I've got a lot of time for linear optics. A lot of time. I think there's substantial, large-scale issues that linear optics has the potential to be a lot better for than other systems. But I mean, so obviously, Sam, you're involved with much more of the large scale. Everybody else, I mean, is this something you think about, or you really? I mean, do you envisage some kind of industry for large scale, or are you still really talking about sort of the smaller active quantum devices that could provide a benefit in very sort of restricted technology spaces?
So, yeah, I guess some part of my research is leading into trying to, there's a small research effort. I'm trying to do analog simulation, quantum simulation, using these photonic devices. And I think that's I think it's an important thing. One, because hopefully these devices can be made big enough but still smaller than you need for universal computation, then somebody out there might find it useful. But I think these stepping stones to useful quantum techs in the short to medium term are really important. I think there's a danger that if we go the next 3 or 4 years, maybe particularly the UK, so the hubs get reassessed and refunded perhaps in the next 3 years. And if by then we haven't got some at least semi-solid results saying here's a quantum device, maybe not in computation, this could be in metrology or QAD, but here's a device, here's it doing something quantum, and here it is performing better and doing something that can do classically. I think that's important, and I think analog simulation or some other kind of simulation is an important stepping stone. Whether photonics is the right platform to do that in, I don't know. I hope so. But yeah, it's an interesting. I don't know. Yeah.
And hey, if Scott Harris or anyone can figure out how to make those on something super useful, then we might be able to have something else.
So I mean, the remit certainly in the first generation of the quantum hubs is for a 5-year funding thing, and that's certainly nowhere near enough time to reach large scale. What do you guys see as potential, really sort of commercial applications of what could happen in 5 years?
So I think QAD is possible. The problem is that getting up to market-ready products is kind of it's like an inverted triangle. To get from base level research up to some prototype is actually, I don't want to say easy, but it involves less less funding, less investment. To go the next level and go from a prototype to something that is ready to sell on the market and ready to produce for industry is really requires the investment of that industry and the time and effort of people that work for them. I think the hubs has been one of the benefits of the hub is that it involves a lot of industry interest, and there's been a lot of industry partners assigned with each of the hubs, which I think is promising. But whether they're keen enough to take it on to the point where we're going to have something useful, I'm not sure, but I think it will be imaging more. Whether they're enough to take it on to the point where we're going to have something useful, I agree with that.
Yeah, I think so. I think in the short term, in terms of commercial application, the thing that's front and center is sensing and atomic clocks.
Because I mean, this is another thing that's also at Bristol. What's it called? QET Labs, which is designed to try and market this stuff and sort of enter this sort of commercial space. I mean, this must ultimately be intrinsically linked to the CDT and to CQP. This must be part of the whole Bristol quantum infrastructure. So I imagine you guys must be, also part of this to a certain degree.
Yeah, the idea of QET Labs is to really create, I'm going to use the buzzword here, and call it an ecosystem. So it's this idea that, I think it's this idea that I just mentioned previously, that doing the fundamental research isn't enough to get something onto the market and get something that people are actually using. You need industry around you, you need to train people to do the work, you need to train people who are going to create startups, start doing enterprises, and you need business investment. So the idea with QET Labs is, so QET Labs encompasses 5 things at the moment, really. One of them is CQP, which is still doing the fundamental research and is the group that is trying to lead at least the photonics side of the research. The CDT also comes under QET Labs. The idea is that we're training people that are still doing fundamental research, but have at least maybe an awareness of where this technology might go and maybe how to progress it to the next stage. And then there's the hubs. So as you mentioned, the hubs are, at least the imaging and the comms hub are very much partly located in Bristol. And then we have these 2 new things one is called QTech, which is the Quantum, so I've written them down so I couldn't remember them yet, Quantum Technology Enterprise Center. So this is a bit like a postdoc CDT, which is supposed to train quantum entrepreneurs and enterprise people, to trying to get people with ideas on how to build startups and businesses, and train them up for a year along with actually Cranfield University. Which is,
so does your CDT program involve these aspects as well, or do you really sort of focus mainly on just the physics and the engineering side?
No, the CDT, we had people come in to talk to us about patents and how what patents are and what IP is and kind of things from IP.
Currently, we didn't get this sadly, but the current CDT year has had an outreach and engagement officer come in and do a whole module on how to engage people with science and how to speak to them in a language that they don't understand, which I guess we're drawn into getting business involved and getting them actually go from the research to something that they can understand how it's useful for them.
Yeah, and one of the CDT doesn't stop after the first year. We actually still have some things once we start our PhD, and one of those is actually funding to go into industry and do a secondment for a few years, for a few months. Sorry. So it's very much the CDT. Yeah, there's the academic side of the CDT. There's the interaction with research groups and supervising stuff. But then there's also this business, these extra skills, these
so
engineering.
How much is this sort of, at least within the Bristol context, sort of ramped up, especially in the last 12 to 18 months? I mean, we've seen heavy investment from Google, IBM. You've seen the IBM investment with the Dutch government. You've seen this $1 billion announcement from the EU. The Chinese have ramped up money. The Australians have ramped up money. This must now turn into quite a thing. to try and keep Bristol competitive and to try to keep Bristol sort of very much within this sort of core infrastructure of what's happening globally. So have you seen these sort of things pick up, and it becomes a lot more important for you guys to get trained into not just becoming, you know, sorry to say, boring old postdocs and academics, but to really try and lead what is hopefully in the next 20 or 30 years going to be an entirely new industry?
Yeah, so I guess QTech is really trying to drive that, and certainly something I'm thinking about when I finish my PhD, whether or not I want to stay in Bristol for a year and get that. And also the group is, as it's folding in resources from the hubs and other fields, we're acquiring people which are not just researchers. So we have a few people now that are just there to work on subsystems, or just there to write really good code for our devices and software. And this is it's really interesting seeing the group kind of morph around us, and you know, it's hard really to draw a line between any of it, and I think that's really good, because there are people that are employed, maybe their main job is to work on this, but they can help out PhD students, and you know, that's a really positive thing to have this kind of interaction. Like you said, an ecosystem.
So, I mean, again, if we can sort of go down the line with each of you, is to, okay, you're going to do your PhDs at CQP and within the CDT. Is academia where you want to move into, or do you think that you can, I personally, I imagine that by the time you guys complete your PhD, the sort of industry foundation of quantum engineering and quantum technologies is going to be much more established, and there's certainly going to be a hell of a lot more places that you guys can go than when I graduated. Sort of again down the line as to, is academia your final goal, or do you see yourself moving into something else? Whether, you know, if it's not quantum related, don't worry. But if it is quantum related but not focused on academia, where do you think things are going to head by the time you're finished?
Yeah, I initially joined. I never ever wanted to be an academic. Well, I never wanted to be a postdoc or a lecturer. I joined because I found the subject interesting. I think the thing that would excite me the most would be seeing this stuff really being used by people that cared about it and people that found it useful. I think by the time it comes to 2 years that we've got left of our PhD, I think that might have moved from academia to industry. I think there'll probably be lots of opportunity, lots of interest in industry in hiring people that maybe we have had the training that we've had in slightly broader kind of knowledge and aspects that we've had. But then, I mean, academia is also great fun, and it's a lovely environment to be in. So actually, yeah, as long as I could continue working on developing technology with a sight of it being useful to somebody somewhere, I don't think I would mind whether that would be in the university or in the company. So
cool. Jana?
Yeah, I'm a bit opposite. When I first started, I had no idea whether to stay in academia or go into industry, but I think I'll probably end up in industry now. Yeah, I think there'll be loads of industry starting up around the time we finish, and it'll be a really good time to get into something. So I think I'd like to do it.
I mean, it obviously gets tougher and tougher. You know, you do postdocs and you're off international for 2 years, and then maybe somewhere else internationally for another 2 years, and it can get a bit tricky. Certainly, if there's an industry avenue where you can stay in the UK, if that's what you want to do, it's probably better.
Yeah, I think it's if I don't go to industry after my PhD, then if I do a postdoc, then I think I'll just end up staying. And I'd like to at least try industry for a bit.
Well, I can tell you from my own experience that it's wonderful to go overseas for 2 or 3 years, but you can inadvertently get stuck.
Yeah.
Sam?
So when I started the PhD, I was pretty set that I was going to stay in academia, primarily because I thought I was going to be doing like some really obscure theory thing that meant that there's no hope in hell that anyone in industry would give me a salary to do it full time.
You'd be surprised.
But hypothetically at this stage, I think I would probably go into quantum algorithms and quantum software, and it's looking like at this stage there are lots of big players that are now slowly building up interest in this thing. So Microsoft and IBM and Google have all got people that are working on developing quantum algorithms and software that can run quantum computers.
Well, there's quite a few startups as well, with places like QBranch and 1QBit and QCware and all these places.
Yeah, exactly. This whole ecosystem is just popping up. So industry might really be a direction from now that I didn't expect even 12 months ago. The things that actually tie me down to academia at this point are like the extra stuff outside of the research. So being able to teach and having flexibility with time.
Sam?
So, yeah, I'm really hoping that someone or some company will come along and think, actually, this photonics thing is worthwhile doing. And that's really what my PhD is trying to show, is that it's not just a beautiful theoretical framework, but actually you can fold in errors and you can fold in all the other, experimental nasties and still get a machine that works. And if we can show that, then, I think that we could get funding potentially in a way that, Google is funding superconducting and other people are funding different technologies. And so if by the end of that there's funding and people starting companies for integrated photonics, then that's definitely something I'm looking into. I mean, if not, QTech would be great, and then there's lots of other, going to live in Vancouver and working for D-Wave isn't completely off the table or really supplying. But or Microsoft or any of these groups, yeah, I just want to make a quantum computer work really well.
I mean, you've mentioned sort of startups, and startups you probably know a lot more about it than I do. Probably one of the smallest, more recent startups is Rigetti Computing in California that's focused on superconducting technology. And they've sort of gone the experimental side with venture money, which, considering the developmental time frame is certain, high risk, high reward. Given your aforementioned interest in startups, I mean, do you think that in 3 or 4 years' time, photonics could be at that precipice where that kind of effort is potentially lucrative?
Yeah, I really think so. I think that people in CQB and QET Labs are really pushing to branch out. We just, I think we were just at the T20 conference, which is lots and lots of CEOs from Silicon Valley type companies representing our technology and what we're doing. And in the Soundcloud, we were really interested in a good show. So we the group and QET Labs as a whole are trying to move into that area, and I would have thought something hopefully will come out of that soon. It's definitely something people are putting a lot of effort into.
Well, it could be your responsibility in 3 years. You never know.
Yeah, that would be fine as well.
So, I mean, we're coming up close to an hour. So the general question that I sort of asked last before we call it quits on the podcast. And as I've said to our previous guests, we come back hopefully in 5 or so years if we're still around. Whoever gets the closest, I'll shout them a bottle of whiskey of their choice. So basically the prediction is, where do you see things being in 5 to 10 years? Where do you think? So today we have things like the quantum experience. We have Martinez's 9-qubit chip. We have the current state of the art at Bristol, whether it comes to these small computing nodes or these other applications with various other systems. So if you were to make a prediction, in 5 years when you guys should have finished or be in first or second year of your postdocs, where do you see it being? Doesn't have to be right, but the person who gets the closest gets a bottle of whiskey over every episode that I do between now and then.
How good is the whiskey?
It's whiskey of the winner's choice.
Oh.
Oh, it's a lot of wine.
Provided I'm not broke.
I think 5 to 10 years. Okay, right. What would I say? I think I would be very happy but very surprised if we had a full error-corrected quantum computer that was doing something that couldn't be done classically in 10 years. I think that would be. Well, I don't know, actually. It's tough. It would be pushing it. I think it's not 5 years, no. 10 years, maybe. I think we're certainly going to see useful small-scale QAD networks crop up in places for And I think certainly I can maybe talk about sensing. I think sensing is at the point where now we understand how to produce the states and how to kind of analyze how useful these states are for different scenarios. And we're really now fishing for people that are doing the experiments in chemistry or biology or in medicine to come to us with the problems that they're having and see how we can integrate and build a system for them. So it's really, that's really the tough point now for sensing is finding the application that really has these kind of limits on the precision and has something that they really want to measure, but they just can't because of some experimental parameter. And if we quantum light into this thing, then hopefully it'll get better. And I think LIGO is a great start, but it's not a huge market given the, or maybe it will be with the, maybe we'll get gravitational sensing pop up everywhere now we can know that we can detect it. But yeah, I think sensing certainly in the next, I would hope in the next 5 years, if we can find the application, I think it would be fairly plausible that we would have these things being used quite regularly by a certain industry.
Okay, so sensing's commercial, large-scale computer hopeful.
Sorry, say that again?
Sensing commercial, large-scale computer hopeful.
Yes. Yes, that's a good one.
So I think maybe we'll have some more D-Wave-like things, but with other platforms possibly.
So you're thinking in a Neela.
Yeah, so but maybe someone doing that sort of thing on a different platform, like maybe even like photonics, but maybe so not quite doing universal or quantum computation, but doing useful things, and maybe a bit, maybe something that are classical. And then we'll try out like hybrid things as well. Right then. Maybe like hopefully some quantum dots and photon sources.
Well, hopefully. Hopefully. just pester Ruth to get onto it more.
Yeah.
Sam?
So maybe I should stick with these things rather than anything else. So from a hardware perspective, I think in 10 years we're probably going to have enough qubits to do one of two things. I think if you want to go down the universal error corrected route, I think you're going to have enough qubits to at least do some demonstration of error correction on a handful of logical qubits. If you're not interested in universal quantum error corrected computation, the hardware is probably going to be good enough to get to a stage that people tend to call quantum supremacy, which is a bit of a horrible buzzword, but just to the stage where you can set up an experiment where the outcome of that device is just something that you couldn't predict classically. So people tend to look at boson sampling, the problem in photonics, but that's not necessarily the only force in that race. There are lots of different problems you can use to demonstrate quantum supremacy over some kind of classical device. So I think that's probably going to get with hardware. In terms of algorithms and software, I think that there's this whole zoo of algorithms that are demonstrating a quantum advantage. You can go online and look them up, and there's
That's the Quantum Algorithm Zoo by Stephen Jordan.
Yeah, exactly. Just go ahead and Google it. There's loads and loads and loads of them. And I think we're going to get to the stage where a lot of those problems start to look less esoteric and start to get translated into a language that demonstrates they're useful for solving real-world problems. So this could be in machine learning, or it could be in fluid dynamics, or it could be in a whole host of different applications. That's what I think will be with software.
Sam?
So I think that in 10 years' time, we hopefully should see Martinez's device going into 2D grid, and with that will come one, maybe not more than one error-corrected qubit, quantum error-corrected qubit, which would be really nice to see and to show that adding this layer of error correction really does give you a really nice qubit that you can hold for a long time. And hopefully, I guess as well, the same with ion traps as well. I'd like to see the PDOT silicon guys really coming along and starting to develop their tech and coming out from behind and kind of scaring everyone in terms of how good they can do stuff. But
so this is the phosphorus and silicon technology from Australia.
Yeah, exactly. I think well, they do show a lot of promise, and if they can, they've recently released a paper to shook things up a little bit and show what they could do, and hopefully they'll be able to strength. Photonics, I think will get some funding, and it will maybe have a startup going, if not more than one. And hopefully with that, it will be able to develop. I don't know if it will have one error-corrected qubit in the same way, but it will definitely, I would have hoped to have a set of the Rausendorf going on, something like that. A good, nice big bit of percolated cluster would be nice, that we can begin to chop up and move into something we can then do that.
Well, I must admit, you're all very pessimistic.
So I hope that our things are weighted, because like a good scientist, we've got to weight how much time we've been in the industry. So what, 2 years compared to Seth-Lloyd's predictions, who's willing for 20, 30. Well,
I've been optimistic for large scale since 2005, so my entire career has been defined by optimism. So finally, is there anything going on at the CDT or the CQP or personally related to science or anything else that you guys want to plug?
I would just, on behalf of the CDT, we've got across the point that we're definitely not, we're platform independent. The idea is that the training is as wide and as thorough as we can be. So if there are people who want to interact with CDT, they want to chuck projects, they want to maybe find out how they can get PhD students, or they want to come in and give a platform, we call them, where you come in from your quantum platform for the device and you talk to the CDT for maybe a day or so, and why you think it's the way to go and why you think it's good. And just go onto, I think the website has lots of email contacts. So yeah, if it sounds like something you can contribute to, or you'd like to maybe get some contribution from, you need to get involved, because it's a good place to be right now.
Anything else? No.
No, thanks for having us.
No, thank you all for joining us. It's been a wonderful little discussion. The audio, unfortunately, has gotten muffled in certain bits, but luckily Sam on the other end has recorded from their side. So once he sends me a copy of that, I'll re-upload the YouTube clip, and obviously the podcast on SoundCloud and iTunes will be updated with the clearer audio. But hopefully it wasn't too bad for those of you who are watching live. But thanks again to all four of you for sitting down for an hour and having a chat on this small little podcast that will hopefully keep going in the weeks and months to come. I'll obviously embed links both to the CDT website, the CQP website, and various Twitter accounts of our participants today. So once again, all four of you, thanks a lot for spending the hour with me.
Thank you.
Cheers.